Our thermochemical adventures continue. Thanks for joining us. So, we are continuing to practice using enthalpy equals number of moles times molar enthalpy. And the recurring theme in these questions is we're not going to tell you what delta H is, so you get to calculate it using products minus reactants. Let's see what we get. They say we have 50 kilograms of zinc sulfide, but kilograms are for power lifters and cocaine dealers, so I'm going to change this to 50,000 grams of zinc sulfide. And we can get a molar mass from this because the only reason we care about masses is for getting molar masses. So mass is the 50,000 we just said. Molar mass is 65.41 for the zinc plus 3207 for the sulfur is 9748. And 50,000 divided by 9748 gives us 512.926. Sorry, I had to think about my rounding. Moles for our zinc sulfide. And our formula says, great, that number of moles is this N. Just multiply that by a delta H and you're done. Tragedy, we don't have the delta H, so one more thing to do. How do we find delta H? Products minus reactants. Molar enthalpy equals 2 zinc oxides plus 2 sulfur dioxides minus 2 zinc sulfides and 3 oxygens. I know none of those numbers, so, well, I know one of those numbers. Let's see what we get out of the data book. 2 times zinc oxide is minus 350.5. Plus 2 times sulfur dioxide, blah, 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 minus 296.8. Minus 2 times zinc sulfide, also known as sphalerite apparently, minus 206. And oxygen 0, you can either write a 0 or just ignore that completely. Mathematically, it's the same thing. Okay, mash your calculator and I'll mash my calculator and we'll talk in a second. 2 times minus 296.8. Negatives cancel, so I can just say plus 2 times 206. If you're comfortable with that, I get minus 882.6 kilojoules for the enthalpy of reaction. For this reaction as written. You know in a minute I'm going to be ranting about how this isn't the delta H that goes into our formula, so prepare yourself for that. Okay, so our formula's been patiently waiting for us to get all our information together. Total enthalpy change is our number of moles, 512.926 moles of zinc sulfide, times, if we want our answer to come out in kilojoules, of course we'll need kilojoules in this unit. Also, something's going to have to cancel these moles of zinc sulfide. And both of those numbers come out of our balanced reaction. It's 882.6 kilojoules for every 2 moles of zinc sulfide. That's not exactly the same way I've said this the other times, but I'm trying to not bore you to death by doing the same rant every time. So, if we calculate all this, 882.6 divided by 2 times 512.926, and I get 226,354.2 kilojoules. Now, this mass only had 3 sig digs. Everything else we were given had more, so we have to trim this answer down to 3 sig digs. The trouble is you can't write 226,000 anything with only 3 sig digs. So we have two options. We can go to scientific notation, in which case we would say 2.26 times 10 to the 1, 2, 3, 4, 5 kilojoules would be a perfectly good answer. Or we can divide this by 1,000, which puts the decimal right there, and we can write 226 with 3 sig digs. So dividing by 1,000 turns kilojoules into megajoules. Either one of these is an okay answer as long as you remember that this first reaction was exothermic. So our answer here should be exothermic. Good. Let's try another one. Calculate the change in enthalpy when 1 gram of iron turns into rust. Okay, so iron reacts with oxygen and turns into iron 3 oxide, also known as rust. That's one of the forms of rust. And this reaction is not balanced, so we'll fix that right away. 3 and 2 for oxygen, our common multiple is 6, so a 2 there gives us 6 oxygens, a 3 there gives us 6 oxygens. But now we have 4 iron, so we need 4 iron over here. And I call that balanced. Hopefully you do too. They said we're starting with exactly 1 gram of iron. That's our mass, of course. The molar mass for iron is 5585. And so our number of moles is 1 divided by 5585, 0.017905 moles. Yeah, okay. So we have our number of moles, and we have this formula waiting to help us that says our enthalpy change is going to be the number of moles we just found times delta H. As usual, they didn't give it, so we get to calculate it. Do you see why this math is going to be pretty simple? When we do our delta H, it's products, Fe2O3 minus reactants. And when we go to our data book for numbers, we get 2 times iron 3 oxide is minus 824.2. Minus 4 times 0 plus 3 times 0 is just 0. So we could have completely ignored our reactants. We would have been fine. 2 times 824.2 is going to be minus 1648.4 kilojoules. That is our delta H. That is our enthalpy of reaction for this reaction as written. Now that we have that, enthalpy equals N delta H equals our number of moles we found before, 0.017905. Molar enthalpy, 1,648.4 kilojoules for every 4 moles of iron. 1648.4 kilojoules for moles Fe equals, calculator keys are punched, divided by 4, 7.379 kilojoules is our answer. This reaction was exothermic, so this should have a minus sign on it, and 3 sig digs is our lamest number, so this should be trimmed down to 3, so actually minus 7.38 is where we come to rest. Not too bad. As soon as they talk about enthalpy in just about any way, you can anticipate you're going to be using this formula, and it's just a question of what information do they give you. If they give you a mass, they've effectively given you the number of moles. If they give you a balanced reaction, they've effectively given you delta H. It just takes some number crunch, and that's enough to find the molar enthalpy. Or, sorry, the total enthalpy. And if they give you total enthalpy, they could have you work backwards and find either of these other things. So, not a complicated formula, though I admit it is a little time-consuming crunching through all this. But you can do it.